Welcome to Ask and Learn.
Okay, so we are asked to find the standard entropy of SOCl2. So the best way to do this would be to plug in the values we are given. So we're given these standard entropies, and then find the delta S of reaction and use SOCl2 as our x and solve for that. So the first thing we want to try to do is find the delta S of reaction. And then once we do that, we're going to be able to plug it into this. So let's just call this equation 1. We'll plug it into equation 1, and we'll be able to solve for the standard entropy of SOCl2. So in order to find the delta S of reaction, we are given the delta G of reaction, and we're given values to find the delta H of reaction. So we can use this equation, let's call it equation 2. So using equation 2, we're going to have the delta S of reaction as our x value there. We'll be solving for the delta S of reaction. And then again, we can go plug this back in to the delta S of reaction. All right, so let's start with the delta H of reaction. So we're given delta HF values for all the relevant molecules here. And by plugging them in, again, we're going to do products minus reactants, and then we will be able to find the delta H of reaction. So I plugged those values in on this line here. So again, these just correspond to these values plugged in. I think it's always helpful to write out the skeleton just so you don't get lost in your calculations. So if you want to pause the video really quickly and do that calculation, you should come out with negative 96.4 kilojoules is our delta H of reaction. All right, so now that we have that, we can plug it back into equation 2 up here. Again, this is equation 2, so we can plug it back in there, equation 2. So we are given that the delta G is negative 75.2. So I plug that in, and then we have our delta H of reaction that we just found, our negative 96.4 kilojoules. And then again, this x, excuse me, I'm having a hard time talking today. This x is going to stand for our delta S value, our delta S of reaction. All right, so if we go through and solve that for x, we should get that our delta S of reaction is equal to negative 0.0711 kilojoules. And remember that all the standard entropies are given in joules. So let's change this into joules. Again, you can do that by multiplying by 1,000, and you would get negative 71.1 joules, and it's actually joules per Kelvin. Perfect. Oh, and sorry, it's actually joules per mole Kelvin. Great. Okay, now moving on. So again, we're going to take, now that we know our delta S of reaction, we can plug that into our equation 1 in order to find our standard entropy of SOCl2. So I've taken the standard entropies we are given, again, using the formula products minus reactants, and we're going to plug in our delta S of reaction over here. This line right here is just the same thing as this, but filled in with the values we are given in the table, just to make that a little more clear. Great, so we're going to plug in our negative 71.1 there, and then we're going to solve for x, which will be our, let me see if I can just write over this, which will be our, oops, that's not what I wanted, standard entropy of SOCl2. So if you want to go ahead and pause the video really quickly to do that calculation, you should get 121 moles, or I am all over the place today, 121 joules per mole Kelvin. Great. Okay, so part B wants us to find what temperature this reaction will be non-spontaneous. And whenever you're asked a question like that, always remember that you want to set this formula to 0. You want your delta G to be 0. By doing that, you can solve for T, which will give you the temperature you are looking for. So again, we found our delta H of reaction. That was negative 96.4. It was in kilojoules. Make note of the units here because we want to make sure we're using the same units on this side. So we're solving for T, so I'm just going to put an X there. And remember, in kilojoules, we had negative 0.0711 kilojoules for our delta S of reaction. And if you solve that out, you should get T equaling 1.4 times 10 to the third Kelvin.